Alright, so let's talk about trigonometric form of complex numbers. So if you have a complex number z, move that here. We'll say it's -4 square root of 3 minus 4i. We'll say that's your complex number, right? The question asks to put this complex number into trigonometric form. Well, what does trigonometric form look like? Well, trigonometric form is going to look like z equals absolute value of z, which is the modulus, times cosine of theta plus, move this down here, I sine of theta, right? So in this case, absolute value of z here, this is your modulus, or the distance from the origin, and it's absolute value because you can't have a negative distance. Now if you look at here inside, at the input of these trig functions here, cosine and sine, the input is the angle, or theta, which we're going to call the argument. Alright, so if you take this and let's graph it to see what quadrants it's in, because that's going to help us a little later on when we're trying to find what the argument is. Right, so if you take this number here, how do you graph it? It's not quite clear at first. What we can do is we can take this and we can have an ordered pair that corresponds to this complex number right here. So it's the ordered pair is going to be in the form a comma b, right? Where a here in this case is -4 square root of 3. That's going to be the real part of z, where here the -4 is going to be the imaginary part of z. Now, -4 may be a real number, but in this case it's the imaginary part of z because it's the part that's multiplied by I. So this is going to be our ordered pair that we're going to graph here. So the x, so this axis, as usually our x-axis is going to be our real axis in graphing complex numbers. And this axis, that's typically our y-axis, is going to be the imaginary axis, where we graph the imaginary part of the complex number. In this case is our -4. So 1, 2, 3, 4. So -4 and square root of 3. So that's going to be probably about right before, it's going to be about here. And then -4, it's going to be on this axis. 1, 2, 3, 4. Actually, no, I counted wrong. It's going to be about here, because square root of 4 is 2, square root of 1 is 1. So it's going to be a little between there. So 4 times 1 is going to be like 4. 4 times 1 point something is going to be a little after 4. So it's going to be right here. So 1, 2, 3, 4. Yep. So then we're going to go down 4. And we know that it's going to be right here. It's going to be our ordered pair. -4 root 3 comma -4. Alright, so then from here we want to find the modulus, right, which is the distance that this point is from the origin. So that's going to be this distance right here. How do we find that? Well, the modulus, we'll say, is absolute value of z is equal to the square root of a squared plus b squared. You might think to yourself that you may have seen something similar to this before, right? Well, that's because you have. So if you think about Pythagorean's theorem, which is a squared plus b squared equals c squared, you're trying to find the hypotenuse, right? So in this case, what's your a term? This, which is this x-axis, so this can be the a leg of the triangle. What's your b term here? -4, so this could be the b leg of the triangle. And then in this case, our c is absolute value of z, because it's the distance from the origin, so it's going to be here, right? So that's why we do that. So our absolute value of z in this case is going to be equal to the square root of -4, or not the square root, sorry. It's going to be -4 square root 3 squared plus -4 squared. So what do we get here? Well, we get 4 times 4 is 16. Root 3 times root 3 is 3. So 16 times 3 is going to give you 48. So you're going to have 48 here, right? Plus -4 squared. Forgot the square up here. So -4 squared. So -4 times -4 is positive 16. So you got that. And then 48 plus 16 is 64, which the square is 64. We know is to be 8, right? So absolute value of z is 8. Just adding the z's, the absolute values of z there, the modulus. So we're trying to find this, right? So far, we'll put it over here. So we have z equals absolute value of z cosine of theta plus I sine of theta. Forgot parentheses there. So far we know the modulus, so let's go there and add it in. 8 cosine of theta plus I sine of theta. Right? So what's next? What do we have left to do? Well, like I said earlier, we want to find the argument, or the modulus, which again is absolute value of z is the modulus, right? Then we want to find theta, which is the argument, right? The input to these trig functions here. So how do we find theta? Well, we know that our theta is going to be this angle here, right? Because we're measuring, well, the angle's theta is going to be this angle. We're going to first find this relative angle, so we can then find this angle. So how we do that is we're going to use our trig function tangent, right? Because we know that tangent of this angle is opposite over adjacent, right? Or sine over cosine. So if tangent of theta is sine of theta over cosine of theta, we know that sine of theta, the opposite, is going to be -4 for the hypotenuse, which is going to be 8, over cosine, which is of theta, which is going to be -4 times the square root of 3 over 8. All right. So how do we divide fractions? Well, we multiply by the reciprocal. So we say this is going to be -4 over 8 times 8 -4 root 3. Let me move this a little bit so you can see it a little better. I'll rewrite it down here because you can't, it's kind of hard to read there. So we have -4 over 8 times 8 over -4 square root of 3. Right? So here, these 8s are going to divide out to be 1. So you have -4 over -4 square root of 3. These also divide out to be 1. So you're left with 1 over square root of 3. So now you have that. Well, what do you do with it? We know that tangent theta is equal to 1 over square root of 3. How does that help us? Because we're trying to find this argument here, right? So, all right, argument. So we want to figure that argument out. So if we think back on our convenient triangles, right, we have 30, 60, 90, and the 45, 45, 90 triangles. So if we look at, all right, let's say this is 30, 60, 90, so we'll say this is 30 degrees, this is 90, this is 60. So across from 60, we have root 3 over 2. Here we have 1/2. Here we have 1, right? So we want to figure out what combination would give us, what combination of tangent of sine over cosine will give us 1 over square root of 3. And then that will be our argument, right? So let's say we have, let's look at it. Let's say potentially it could be tangent of pi over 3 or 60 degrees. So if we have tangent, let me draw a line here, tangent of pi over 3 will give us root 3 over 2 over 1 over 1/2 over 1, or just root 3 over 2 over 1/2. Which will give us root 3 over 1, right? And that's, what is this? 1 over root 3. This is root 3 over 1, so clearly that's not what we want. So let's try tangent of pi over 6, or 30 degrees. We have 1/2 over root 3 over 2. So let's say 1/2 over root 3 over 2. Flip and multiply, we get 1 over root 3. Is that the same as this? Yes, that is the same as this. So our argument is going to have to be pi over 6. So argument is equal to pi over 6. So now that we know our argument and our modulus, we can completely put it into trigonometric form. So we get a new paper, and we'll say, we'll set this paper aside, and we'll say, we'll write down our original problem, right? It equals -4 square root of 3 minus 4i. And we want this in trigonometric form, which is in the form of z equals absolute value of z with a modulus cosine of theta plus I sine of theta. And we want to put this into, well, we want to plug in all the things we know. So we know the modulus, or absolute value of z, is 8. And we know that the argument here is going to be pi over 6, which is 30 degrees, plus I sine of pi over 6. And like we know it's 30 degrees, so we could also have written it z equals 8 cosine 30 degrees plus I sine of 30 degrees. And that's it. There you go. And that's how you find the trigonometric form of complex numbers.